Hello friends, welcome back. Now we'll be looking at a few questions on matrices. We'll try to cover as many different concepts as possible. So the first one, if A, B, C and D are real numbers and A is a matrix here, so it's written as A, B, C and D, prove that A square minus A plus D into A plus AD minus BC into I equals 0. Now here I obviously is an identity matrix, and unless stated otherwise, in these kind of questions, whatever the order of the matrix A is, that should be the order of I. So it is of order 2 here, right? I2. So let's get going with this question. First of all, I write what my A is, which is A, B, C and D, right? So I now try to find out A square. So we multiply matrices using the formula we know. Right? So this is A square plus BC, the first term. The next is AB plus BD. The next is AC plus CD. And the last one is BC plus D square. Right? So now we know our A square, we obviously know our A. I is simple, 1001. Right? So let us try to expand our left hand side of this required statement. So let us try to expand A square minus A plus D into A plus AD minus BC into I. Right? So my LHS is A square minus A plus D into A plus AD minus BC into I. Right? This is, what is A square? A square plus BC, AB plus BD. AB plus BD, similarly AC plus CD, and then D square plus BC. Right? Minus A plus D into A is ABCD plus AD minus BC into 1001. Right? Now, first of all, for the second and the third terms, we use scalar multiplication, and finally, we just add them using our simple addition and subtraction, right? So I'll try to write all of these in one step. Follow carefully. And this first is, for the first one, A square minus A square plus BC. For the next one, I have minus of A plus D into A, and then for the last term, I have plus AD minus BC. Right? So this is just my first term, or the first element of my required matrix. The next one is AB plus BD minus A plus D into B. The last term is 0, so just this much. Then the third one, AC plus CD minus A plus D into C, and again 0. Right? So moving to the last one, D square plus BC minus A plus D into D plus AD minus BC. Right? So this is the whole thing. Now, if you try expanding this is A square, and then we have minus A into A, right? So this A square and this A square cancels. Then I have BC here, minus BC here. I have minus AD here, and this is plus AD, right? So 0. Similarly, AB, expand this, and you have A into B, so this cancels. Then you have BD, and this also cancels. Similarly, AC, CD, CD cancels, right? So, and here to D square, and you have D square here, BC, minus BC here, AD, and plus, minus AD and plus AD, right? So you see that everything cancels, and this can be written as just 0. 0 is the null matrix here, or the 0 matrix, and again 0 just corresponds to the 0 matrix of the same order as the other matrices in the question. Right. So we see that this is indeed 0 and hence we prove it. The next one, if A is equal to 1, 2, 2, 2, 1, 2, 2, 2, 1, find A square plus A minus phi I. Okay. Now, once we know A, we'll directly set out to find out our A square. So, A square is just this matrix multiplication of A, which is 1, 2, 2, 2, 1, 2, 2, 2, 1, right? So, this is 1 plus 4 plus 4, that is 9. Then I have 2 plus 2 plus 4, 8. Similarly, 2 plus 2 plus 4, 8. Actually, using symmetry, you can see that even the next term will be 8. This is 9, this is 8. These two are also 9, 8, and this is finally 9. Right? Better not to take such chances, and you should try to solve all this completely and correctly in exams. There might be a few some silly mistakes may creep in, so just try to check them. So now that we know A square, let us just try to expand our given statement. So that is A square plus A minus phi I. Right. So A square plus A minus phi I. Obviously I is the identity matrix of order 3. So A square now is 9, 8, 8, 8, 9, 8, 8, 8 and 9. Right. Plus A is 1, 2, 2, 2, 1, 2, 2, 2, 1 minus 5 times of the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Right. Now this is nothing but 9 plus 1 minus 5, that is 5, right? Similarly 8 plus 2, 10 minus 0, that is 10. And then again 8 plus 2 minus 0, 10. Similarly 10. Again 9 plus 1 minus 5 is 5, 10, 10, 10, 5. Right? Once you get this, you may actually stop here, but if you look closely, this is nothing but our original matrix A multiplied with 5, right? If I try to take 5 common from everything, from all the terms, I have this as actually 5A, right? I take 5 common, so this is nothing but scalar multiplication. So if I try to divide the whole thing by 5, I get back my original matrix A, right? So this is actually equal to 5A. Oh, sorry. Right. So the question the answer can actually be left at this matrix, but it's better to actually write it in this format, 5A, right? Okay. So the next one now. If A is equal to 0 minus tan theta by 2, tan theta by 2, 0, and I is equal to 1, 0, 0, 1, show that I plus A is equal to I minus A into cos theta minus sin theta cos theta. Okay, now this is, if you look at this question, the statement here, right, the statement we are supposed to prove actually has more complex terms on the right hand side than on the left hand side, and usually it's the other way. So we will, instead of going on a traditional way from left to right, we will try to go from right to left. Okay, because left has relatively simple terms, just the addition of two matrices. So we will try to first of all subtract A from I, and then multiply that with the matrix given here, cos theta minus sin theta cos theta, and see if we can link it to I plus A. Okay. So the RHS here is I minus A cos theta minus sin theta cos theta. Now if you look at the question, actually you have tan theta by 2, right, in as A. So that itself indicates that there has to be some kind of some kind of manipulation of or some usage of trigonometry formulae. So this is actually how, or this is actually a classic example of how trigonometry is blended, or different parts of mathematics are actually just mixed into and formed as one question. That is why you should be good with all the different parts of mathematics, right? So because as you see in this question, we'll be using a very important formula of trigonometry to solve this question, without which this question is just not possible, right? This is okay, 1 0 0 1 minus 0 minus tan theta by 2 tan theta by 2 0 this into cos theta minus sin theta cos theta, right, which is 1. The sign changes for a, so I have minus here, minus tan theta by 2 and again 1 multiplied with cos theta minus sin theta cos theta, right. Now what I do is, the first matrix here, I see that I have tan theta by 2 here, right. Now tan theta by 2 is nothing but sin theta by 2 by cos theta by 2. So what I do is, I multiply this matrix by cos theta by 2, I multiply its scalar by scalar cos theta by 2. At the same time I have to divide by cos theta by 2, right, to maintain its value. So what I do is, I multiply by cos theta by 2, I also divide by cos theta by 2. So I'll just keep the cos theta by 2, the division part aside first. And now once I multiply it by cos theta by 2, I have for the first term cos theta by 2, right? Similarly for the fourth term 1 cos theta by 2. And now for the second and third terms, I will have sin theta by 2 and minus sin theta by 2 respectively, right? So I have cos theta by 2, sin theta by 2, minus sin theta by 2, cos theta by 2. This multiplied with cos theta minus sin theta, sin theta, cos theta. Right. So let us just expand and multiply. So I have cos theta by 2 into cos theta plus sin theta by 2 sin theta. Similarly minus cos theta by 2 sin theta plus again minus sin theta by 2 cos theta plus sin theta cos theta by 2, and the final term sin theta by 2 sin theta plus cos theta by 2, right. Now if you look at all these elements, now what are they? They are nothing but they can be reduced to simple formulas, right? So look at the first one. This is nothing but cos of a plus b formula, a minus b formula, right? So since there is a plus here, so actually I should just be confused, so I'll just remove that part. Now since there is a plus here, this plus, hence this must be cos of a minus b formula, right? Cos of a minus b here, a can be either theta or theta by 2, right? Doesn't make any difference because cos is an even function. So this is cos of a minus b, that is cos of theta minus theta by 2, or it is just cos of theta by 2, right? The cos of minus theta by 2 is the same thing as cos of theta by 2. Similarly, look at this. This is sin of a minus b formula. Now obviously we have a few restrictions here. A has to be theta by 2. A cannot be theta, right? So this is minus sin theta by 2. Why minus? Because you get theta by 2 minus theta, which is minus theta by 2, and sin is an odd function. So sin of minus theta by 2 becomes minus sin theta by 2. Now for the third one, actually this is sin theta by 2 with the same analogy. And the final one is again cos theta by 2. Right. Now I have this scalar here, right? Cos theta by 2. So I just divide the whole thing by cos theta by 2, or just multiply the whole thing by 1 by cos theta by 2. So what I get is 1 minus tan theta by 2, tan theta by 2 and 1. Right. Now look at your expressions. Now I can easily expand this as right? 1 0 0 1 plus 0 minus tan theta by 2, tan theta by 2 and 0, right? The first one being I and the second one being A, right? So which is equal to my LHS, right? So we see that here just the knowledge of matrices will not be useful unless you also know trigonometry and those basic and important formulae thoroughly. Okay. The next one here, A is a 4 by 4 matrix with these elements. Now if trace of A is equal to 0, find the value of X. So it's a fairly simple one. We know what trace of a square matrix is, right? So it's just the sum of the principal diagonal elements, and that the value has been given as 0, right? So we just try expanding it. And this is equal to 0. Now just simplify this. So you have 2x square, 2x minus 12 equal to 0, right? 2 can be taken common, so I have x square plus x minus 6 equal to 0. Well, this is nothing, the roots are nothing but 2 and minus 3. Right. That's it. Find the value of x and you know that x is either 2 or minus 3. Okay. Now, determine the values of alpha, beta and gamma when the matrix 0, 2, beta, gamma, alpha, beta minus gamma and alpha minus beta gamma is orthogonal. Now, here is where definitions of few special matrices should be known. Now, what orthogonal means is A transpose into A or A into A transpose. Both the now an orthogonal matrix is also commutative, so both of them are fine. That is equal to actually I, right? So I have A into A transpose is equal to A transpose into A, which is equal to I, the identity matrix of the same order, right? So I take either of them and I try expanding it. So this is now 0, 2 beta, gamma, alpha, beta, minus gamma, minus beta, gamma. So this is my A. Now I write the A transpose 0, 2 beta, gamma, alpha, beta, minus gamma, alpha, minus beta and gamma, right? Okay. Now once this is done, I'll just expand this. Okay. This is 0, 2 beta square, 2 into 2 beta, that's 4 beta square plus gamma square. The next term is 2 alpha beta, minus 2 beta square plus gamma square. Just a second. Okay. So the next one is 0 into alpha plus 2 beta into 2 beta, that's 2 beta square minus gamma square. Right. The next one is gamma square minus 2 beta square. Right. And then we have alpha 2 beta, again 2 beta square minus gamma square. The next term is alpha square plus beta square plus gamma square. And then alpha square minus beta square minus gamma square, right? Finally, again gamma square minus 2 beta square, alpha square minus beta square minus gamma square, and then alpha square plus beta square plus gamma square, right? Now this is our A into A transpose, and this is since it is known that A is an orthogonal matrix, so we know that this is equal to 1 0 0 0 1 0 0 0 1, right? So now we know that these two matrices are equal to each other. Now what that means is all their individual elements are actually equal to each other, right? So all the corresponding elements are equal. Now equating them, we get a few conditions, and since we have three unknowns, so we need at least three equations. The first one is we compare this one, right? This and this. So I have alpha square plus beta square plus gamma square is equal to 1. Then I take this one. So I have 4 beta square is equal to plus gamma square is equal to 1. And finally I take this one. Right? Or actually it's better I take this one. So I take 2 beta square minus gamma square. So I'll not take this one, at least for now. So I'll take 2 beta square minus gamma square is equal to 0. Right? So I'll take this one. Now 2 beta square minus gamma square equal to 0 gives me simple gamma square is equal to 2 beta square. Right? Now I put this in this equation, and what I have is 4 beta square plus 2 beta square is equal to 1, which gives me beta square is equal to 1 by 6, right? Or further, beta is equal to plus or minus 1 by root 6. Okay, both of them are perfectly fine. Now once I know beta, I can easily find out gamma. Beta square is 1 by 6, so gamma square is 2 by 6 or 1 by 3. So that is gamma square, sorry. And hence, gamma is equal to plus or minus 1 by root 3. Now I know both beta and gamma. Put them in the first equation. What you have is alpha square. Okay, I'll just directly take them to the. Okay, fine. 1 by 3 plus 1 by 6 is equal to 1. Or alpha square is 1 by 3 plus 1 by 6 is 1 by 2. So alpha square is also 1 by 2. And hence alpha is equal to plus or minus 1 by root 2. Okay, so I get my values here. So alpha is plus or minus 1 by root 2, beta is plus or minus 1 by root 6, and gamma is plus or minus 1 by root 3. Right? Now, be careful here. So there are actually 8 possible solutions here, right? Alpha equal to plus 1 by root 2, and then changing the sign of beta and gamma, right? Both for both plus or minus are perfectly fine. Similarly for alpha equal to minus. So since the signs are completely independent of each other, there are total 8 solutions here. I mean just so if this question is asked. Okay. Now the sixth one. Find the symmetric and skew symmetric parts of the matrix A is equal to 1, 2, 4, 6, 8, 1, 3, 5, 7. Right. Now this is a very important part. Well, actually this comes from a property which states that any square matrix A, right? So any square matrix can be written as the sum of a symmetric as well as skew symmetric part. Sum of symmetric and skew symmetric matrix. Right. So how exactly do we do that? So there is a very simple way to do that. So it's just that what that property means is that any matrix can be represented as a symmetric part and a skew symmetric part. The symmetric part is given by half of A plus A transposed. Right. So this is the symmetric part. Now it's a very simple property and very easy to even prove. So I leave that to you if you're keen to see how it actually works. So I'll just go ahead with the question here. So A is 1, 2, 4, 6, 8, 1, 3, 5, 7, and I have A transpose as 1, 2, 4, 6, 8, 1, 3, 5, 7. Right. Now this is add them up. Now obviously if you anyway know that a symmetric element So this will be nothing but like 1 plus 1, so this is 2, 2 plus 6, 8, 4 plus 3, 7. Now obviously you see that since it is symmetric, well actually you can verify it that way. So this is also 8 and this is also 7, right? So this is 16, this is 6, so is this 6 and this is 14, right? So you can see that this is actually symmetric matrix, though this is not my symmetric part, right? This into half is my symmetric part. So I divide that. My bad here. This is 4, this is 7 by 2, 3 and 7, right? So you can see that this is a symmetric matrix, and this is nothing but the symmetric part of our given matrix. Now the skew symmetric one, yes, this should be easy to guess. What you can do is, you can just subtract the symmetric part from the given matrix A, or you can just use this formula, half of A minus A transpose. Okay, now in the previous one, the order did not matter because it's just the addition, but here the order matters, right? It's A minus A transpose. This is half of 1, 2, 4. 6, 8, 1, 3, 5, 7. Right. So this is 1 minus 1, obviously it has to be 0, right? Skew symmetric matrix, all the principal diagonal elements must be 0. Right, so I can directly write this way. Anyway, so 2 minus 6 is minus 4, and if you see 6 minus 2 is plus 4, right? So satisfying that condition also, these parts will be just the negative of each other. Similarly 1, minus 1, minus 4 and 4. Right, so this is now 0, minus 2, half, 2, 0, minus 2, this is minus half, this is 2. Right, so this is my skew symmetric part of my matrix. Now if you actually look at it, this will addition of the symmetric and the skew symmetric will actually give you back your original matrix A. Right, so that is why they are known as the symmetric and skew symmetric parts. It's simple form. You can also look at the formula also, right? Half of A plus A transpose plus half of A minus A transpose. Right, so A plus A transpose plus A minus A transpose gives you 2A, multiplied with half gives you A. Okay. The next one now, find the possible square roots of I2. So I2 is the identity matrix of order 2 here. So my I is 1001. Now if the square roots must be of the same order, right? Because let A be the square root, that means A square is actually equal to I, right? Now A square is obviously of the same order as A, and if A square is equal to I, which is of order 2, hence A must be of order 2, right? So now that I have established that A is of order 2, I just take any general 4 elements A, B, C and D, and I try to find out what A square is. So A square is, it's simple, it's so it's A square plus BC plus B into A plus D, C into A plus D, D square plus BC. Right? Now I know that my A square is nothing but I. So what I do is, I write down my 4 equations. The first is A square plus BC is equal to 1. Right? This must be equal to this one. Similarly, B into A plus D is 0. So is C into A plus D. and finally d square plus bc is also equal to 1. Right. Now solving this set of equations may look a bit difficult also and a bit complex too, but we can approach it in a very nice way. First of all, what I do is I look at the second and third equations, right? Both of them have the factor a plus d. So what I do is I assume that a plus d is 0, right? So I take the case where a plus d is equal to 0, right? So this is my case here. Well, that directly gives me that d is equal to minus a, or d square is equal to a square, right? So now what I do is, so d is equal to minus a, and I just take I just assume any random value of a. So I take a is equal to actually alpha, that gives me d is equal to minus alpha, right? At the same time I assume b equal to beta and c is equal to gamma. Okay. Now substituting in any of the remaining two equations actually gives you the same thing. Alpha square plus beta gamma is equal to 1. Right. So any matrix satisfying the condition alpha square plus beta gamma is equal to 1. Right. So any matrix A such that alpha, beta, gamma and minus alpha satisfying this condition will be the square root of our identity matrix I. Right. So we just have to find out any three numbers alpha, beta and gamma such that alpha square plus beta gamma is equal to 1. Okay. Now let us look at the second case when a plus d is not 0. Right. So that directly gives us that b is 0, at the same time c is 0. Right. So a plus d is not 0. So that means b is equal to c is equal to 0. Now once I know that b and c are 0, I put them in the first and the fourth equations, and what I get is a is equal to plus or minus 1, b is equal to plus or minus 1. Right? Now, and hence I get that these are my possible roots. Okay. At the same time, we can also have 1 0 0 minus 1 and minus 1 0 0 1. Right. So I have these obviously plus or minus. So since they are independent of each other, you can just check it yourself. Right. So multiply. These are all those different possible solutions as square root. So all four of them are square roots. Okay. Moving to the next one. Now, if A is equal to ABC, BCA, CAB, where ABC are real positive numbers, ABC is equal to 0, and A transpose A is equal to 1, find A cube plus B cube plus C cube. Okay. Just a second. This real part is not needed here. Right. So just check this out. So ABC are just real numbers, right? Nothing about their positive or negative part. Okay. Right. So I have my A. If you look at it, you can see that it's a symmetric matrix here, and hence A transpose must be equal to A itself. So my condition that A transpose A is equal to 1 or I, right? The identity matrix reduces to A square is equal to I. So A is actually an orthogonal matrix, not of much need to us anyway. So I'll just write A square, A B C B C A C A B, right? So this is A square plus B square plus C square, the first term. Then I have AB plus BC plus CA. Similarly, AC plus BA plus BC. again BA plus CB plus AC, finally B square plus C square plus A square, again BC plus CA plus AB, right? So these things actually keep continuing, AC plus BC plus AB, again AB AB plus BC plus CA, and finally again A square plus B square plus C square. Right, now this is nothing but my identity matrix 1 0 0 0 1 0 0 0 1. Right, so if you actually look at it, you have only two different expressions here. The principal diagonal ones are all of them A square plus B square plus C square, which is equal to 1, right, by comparison. And all the other remaining 6 terms are AB plus BC plus CA. Alright, so I have A square plus B square plus C square is equal to 1. I also have AB plus BC plus CA is equal to 0. Right, now this is where a bit of our algebra comes to help. So I have this condition AQ plus BQ plus CQ. Okay, we will go to this later on. First we'll try to find out what A plus B plus C whole squared is. Right, so A plus B plus C whole squared is nothing but, let's try expanding this. This is nothing but A squared plus B squared plus C squared plus 2 times AB plus BC plus CA, right? Okay, now let us put the values here. So A squared plus B squared plus C squared is 1, whereas this is 0, right? So my A plus B plus C whole squared is 1, right? Now that gives me A plus B plus C is plus or minus 1, right? So now that I know this, let us try expanding or writing a very important formula of AQ plus BQ plus CQ, which goes like this. AQ plus BQ plus CQ minus 3ABC is equal to A plus B plus C into A square plus B square plus C square minus AB minus BC minus CA. Right. So now I also know that ABC is equal to 1. I know that A plus B plus C is actually plus or minus 1. So there are two different cases here. And then A square plus B square plus C square is equal to 1. Obviously from our expansion we found this out. Right. So I put all of these values. What I get is, so I take the 3ABC to the right side. I have 3. Now plus or minus 1 into 1 minus 0. Right. So this is 3 plus or minus 1. And hence, if A plus B plus C is equal to 1, I have this is equal to 4. Right. Oh, sorry. And 2 if A plus B plus C is equal to minus 1. Right? So there are two possible cases here. If I know that the sum of my numbers ABCA is 1, so the value of AQ plus BQ plus CQ will be 4, whereas if it is minus 1, it will be 2. Right? So that concludes the questions for matrices. Now one point here, first we have omitted some of the most important parts of matrices, known as inverse of a matrix, adjoint of a matrix, right? So these things have been intentionally left for the next video, determinants, because the definition of these things has a lot of they're completely intertwined with determinants, so one cannot be done without the other, right? But determinants need a basic understanding of matrices first. So adjoint and inverses and further solution of linear triangles using matrices. Right? So all these concepts topics have been left for determinants chapter, where we will be covering these as well and solving the questions pertaining them. Right? Thank you for watching this video. Stay tuned for the next one.